In this project, an MRI simulator is implemented and the case-based data is simulated. The brain image of subject 4 from BrainWeb database is used as the run-through image. This T1 weighted image was reconstructed many times using line-by-line reconstruction, both ideally and non-ideally. In the ideal case, the resolution was changed and the effects are observed. In the non-ideal case, both the resolution and the parameters you see are changed. The obtained image from the database had given parameters of TE as 9.2 milliseconds, TR as 22 milliseconds, and the flip angle as 30 degrees. Since they were given beforehand, these parameters and their effects are not the scope of this project. During the reconstruction process, concepts of 2D Fourier transforms were used. Brief explanations of the concepts of MRI, such as inhomogeneity, chemical shift, the required formulas for reconstruction, the reconstruction process, explanation of the MATLAB code for reconstruction, and the discussion of the results will be provided throughout this presentation. Here is the layout for the method section. Magnetic field throughout the object that is desired to be scanned is supposed to be constant during MRI scanning. In reality, it does not behave as a constant due to spatial changes that create an homogeneity in the magnetic field. There are three sources of fluctuations of concerns in MRI, which are magnetic field inhomogeneities, magnetic susceptibility, and chemical shift. Magnetic susceptibility refers to the material property that decreases or increases the magnetic field within the material relative to the surrounding field. Magnet homogeneity directly relates to the image quality and various artifacts. The types of problems associated with poor magnet homogeneity include shading, spatial distortion, blurring, intensity loss, curved slice profiles, and zebra banding effects. Chemical shift is a measure of change in normal frequency, which refers to the rate of precession of the magnetic moment of the proton around the external magnetic field due to the chemical environment of the image nucleus. Chemical shift is usually expressed in ppm. For example, the hydrogen nuclei in fat are shifted down by 3.35 ppm from those in water.
For the ideal reconstruction, 2D Fourier transform of the image was taken to observe case-based transformation of the image. Since the resolution is crucial, first, according to the predetermined step size, the equation given, which was obtained from the lecture notes, was implemented in MATLAB. Then, inverse Fourier transform of the case-based data was taken with a built-in function of MATLAB to reconstruct the image. The procedure will be further explained in the MATLAB part. In this part, a non-ideal magnetic field matrix that decreases in the x direction was created to simulate the non-ideal behavior of the inhomogeneous magnetic field. You can see the created matrix from figure 3. After the implementation of non-ideal B0 matrix, image was reconstructed with B0 inhomogeneity. In this part, similar steps to the ideal reconstruction were followed. The formula for implementing non-ideal reconstruction with B0 inhomogeneity can be seen below. Since the white matter is a fatty tissue, chemical shift phenomenon can be observed in this area. To select the white matter, ROI ellipse function was utilized in the selection of the white matter on the displayed image. A map of the white matter in the image was obtained as given in figure 4. According to the white matter map of subject 04, non-ideal reconstruction was achieved. Reconstructing the image by taking both non-ideality effects into account is achieved by implementing the following formula in MATLAB. Next few slides are the results of the MATLAB simulations. Full width at half maximum is implemented as the resolution, and as it increases, meaning it is getting closer to 1 by 1, it is expected to obtain a clearly reconstructed image. From the figures, the results meet the expectancy. As the resolution increases in the MRI simulator, the reconstructed image is getting cleaner. However, the simulation time increases. Overall, this implementation of the simulation was successful. Gx is the gradient of the x-axis. It affects the shift of the voxels, which were exposed to non-idealities. Expectance is that Gx and the shift of the pixels under non-idealities are inversely correlated. It is indeed the case. The results obtained are exaggerated, which is not likely to encounter in real-life scenarios. To implement the chemical shift non-ideality to the simulation, white matter of the brain is chosen. However, in real-life situations, chemical shift effect is observed in every aspect of the image, where a variation between tissues exists. Other than that, the simulation results meet the expectancy. With the presence of the shielding constant, the fatty tissue was shifted and the separation between the fat and water was distorted. Exaggerating the shielding constant made this effect more obvious. Implemented B0 inhomogeneity matrix changes only in the x-axis. Therefore, this non-ideality cannot represent the real-life magnetic field distortions by itself. However, the simulations made with the given matrix resulted in expected results. Since the matrix was inhomogeneous, shift in the x-axis became smaller as x increased. As we changed the scalar multiplier of the inhomogeneity matrix, distortion grew bigger as expected. Overall result of the simulation was satisfying the expectations from the simulation. And here are references.
Since image reconstruction takes time, obtained images were saved to a directory for later use. As mentioned in the introduction section, the T1-weighted brain image of subject 4 was taken from the brain web database, and it was used as the ground truth image. This image was a 3D 256 by 256 by 181 image originally. First, in the MATLAB simulations, for comparison reasons, the ground truth image was displayed after it was converted to a 2D image by fixing the z component of the image to the mid value of the maximum z value. This way, a cross-section image of the brain of subject 4 was obtained. In the constants part, we defined values like full width at half maximum, field of view, shielding constant, etc. as the constants that we arbitrarily changed through the project. We started with 3 mm full width at half maximum to generate the images faster. The next part is the relations part, where we define the relations between the defined constants. Following part is the ideal reconstruction, where we reconstructed the original image according to the constant values defined in the previous part. In this part, we manually take the Fourier transform without using the fast Fourier transform function of MATLAB. We did not introduce any non-idealities. Thus, we obtained another ideal image after taking the inverse Fourier transform. An alternative way of image reconstruction with varying resolutions was written in order to check the result of this part. After the reconstruction of the ideal image, we started white matter mapping, which will be used in the chemical shift. To map the white matter, we used the ROI ellipse function and selected minimum value pixel as the threshold for the white matter selection. Then the original image's pixels were compared against the thresholds and binary mapping took place, which resulted in the white matter map. Before starting non-ideal reconstructions in the B0 inhomogeneity map part, we defined an inhomogeneous B0 matrix, which represents a linearly decreasing magnetic field along x-axis. In the non-ideal reconstruction with B0 inhomogeneity part, we used the reconstruction formula with the B0 inhomogeneity matrix. The process was similar to the ideal reconstruction. In the next part, we only used chemical shift inhomogeneity without B0 inhomogeneity. The simulated a further shift in the indexes of a white matter map to simulate the chemical shift. In the final part, both inhomogenities were applied to the image. The way it was implemented was feeding the resulting image of the B0 inhomogeneity part to chemical shift reconstruction formula. The resulting image was affected by both inhomogeneity and its implementation. Now we will run the code to show the results. Due to time constraints, the simulation will be done with 3 by 3 full width at half maximum.